Devendra Das Sharma is the Intel Fellow in the Data Platforms and Artificial Intelligence Group and Chief Architect of the I/O Technology and Standards at Intel. He is also on the board of directors for the PCI Special Interest Group, working on the PCIe specification, and he co-invented the Chiplet Interconnect standard UCIE and is the chair of the UCIE consortium, which he will talk about. So welcome, Devendra.
Thank you. So, Deepak talked about experience in terms of chiplets, and I'm going to talk about a standardization effort right now in the industry called Universal Chiplet Interconnect Express, UCIE. So with that, it starts with Gordon Moore back in 1965 in his seminal paper where he predicted Moore's law. He also had talked about the day of reckoning, and we believe that day is here. As you could hear the previous speaker talk about how they are building components out of multiple chiplets. That's pretty much pervasive across the industry, and UCIE is our attempt to get some standardization in that process. So we talked about earlier today there are two considerations primarily why a lot of people are doing chiplets, and most of them are proprietary, and that is we are up against the reticle limit, and the other one is the yield consideration. So fundamentally these are things that are functionality that are similar. For example, you can create a larger number of core dies by having small chiplets with lesser number of cores, and then stitch them together at a package level. So those are like the scale up, what I would call a scale up kind of usage model primarily. And there are other benefits, which is what we would call like the heterogeneous integration of the chiplets. And those are around, of course, you're going to get your time to market. In addition to the scale up usage model, you're going to get reduced time to market. It will lower your portfolio cost because you can have optimal process technology for the right functionality. Smaller dies yield better. As we'll see next, IP porting costs are they're exploding in the sense that the same IP, if you take from one process node to another process node, all the cost of having to validate it, port it, all of that, those costs are going up. And overall, it reduces the SKU cost. But most importantly, what chiplets enable us to do, as shown in the picture on the left there, it enables us to offer a bespoke solution. In other words, you can have a set of cores there. You can have different accelerators, different numbers of cores and accelerators. You can have different amount of memory. As long as those are all standardized, you can now think of it as things that we do today already at a board level, right? You can have X number of processors, you can have Y number of your devices, and that can be different for different people. Those can be PCIe devices, CXL devices, what have you. You can have some amount of memory, and the amount of memory can vary between different usages. You want that same capability within the package. And basically UCIE's vision is we want to enable that kind of heterogeneous integration and have an open chiplet ecosystem the same way that we have done with things like PCI Express and CXL. So there are a few things to consider. There are important things, very important things for any kind of a industry-wide initiative to be successful. And we base this on, decades of learnings from multiple people driving very successful industry standards like PCI Express, CXL, USB, NVM Express, so on and so forth. On one side, you have the key metrics, right? So these are the key performance indicators. We call them KPIs. Things that are measurable, right? Things like, bandwidth density. These are like solving real engineering challenges, problems, things of that nature. So how much of bandwidth density we can provide, right? With in a chiplet kind of an environment. What's the energy efficiency? So these are the types of things, and not just energy efficiency from, your TDP kind of a usage, meaning, I get the full bandwidth, how much power I'm burning, but also if I didn't use the full bandwidth, how much power am I burning? Is my power consumption a function, right? A linear function ideally of the bandwidth usage, right? Those are the types of things that matter in these kind of environments. What's the latency, right? I mean, accordingly, you're going to decide what functionality to partition and what not to partition. And of course, things like channel reach, reliability, and availability are extremely important. And of course, cost, right? And we offer both standard and advanced packaging. The other angle of that is around interoperability, right? So, okay, so we define the best indicator, but what does it cover? Is it like a full stack? Can I design something and plug it in the same way I can do today with PCI Express or CXL, right? It's a well-defined spec, end-to-end everything. You just design your part. You don't have to know who is designing the other side, right? There are, like, if you look into something like a PCI SIG consortium, it's 900 member companies. It's impossible for two sets of companies to be talking to each other and designing a part that will just work between them, right? So it's a fully open kind of an ecosystem with everything being defined very precisely. Different usages and different segments. Those are all important, right? Because when I design something, I don't want to be, I mean, some people will design to be a niche, but a lot of people would like their design to go broadly because that's how you're going to recoup your investments, right? Same thing around the technology, right? I mean, you need to interoperate across a wide range of technology, across a wide range of packaging options. All of these things are important, right? So it's the underlying technology, it's the adoption criteria, it's the interoperability, and do you also have like a good, what I would call like compliance and interoperability story, right? So these are the factors that makes successful standards. So in order to jumpstart UCIE, we Intel donated the first specification, completely well-defined specification, about 300 pages. And it's a layered approach, right? Just like any other standard, right? You can see the layers over here. Physical layer is basically standard, TX-RX stuff, clocking, lane reversal, lane repair, link training, everything being comprehended there. Sideband, we comprehend the sideband up front. Then you got the die-to-die adapter, which is, it can multiplex between multiple protocols. There is CRC, retry, all of that comprehended. All of those things gets into that. So that's the equivalent of the link layer. So, and we also notice that we define the interfaces very carefully, which are very well specified interfaces. So that way you can get these IPs from different providers and they're going to just plug and play. And then on top of that, we got the protocol layer, which is for now we are mapping CXL and PCIe. Why CXL and PCIe? Well, because those are the ubiquitous standards. People know how to design to them. A lot of your SoC construction issues, they get addressed by having PCIe or CXL. All people know how to make these interfaces work. All that they need is a voltage supply and a clock, right? And then off they go. And then you got usage model point of view. You got IO kind of usages, whether it is a NIC, whether it is any kind of storage expansion. PCIe or CXL.io is great for those. If you have memory kind of usages, you got CXL.memory that covers it. If you got accelerator kind of usages that wants to play in the coherent memory space, you got CXL.cache, right? So we got those usage cases covered. Very well defined specification with compliance and interoperability defined. And we have two swim lanes. One of them is the 2D standard package, and the other one is a 2.5D. And you can see at the bottom, there are 3 different pictures coming from 3 different companies, right? So what it means is that the way we have defined things, it interoperates. You can design your dies to those, anywhere, and you can bring them and you can package them anywhere, and it just is going to work. And this journey is just starting, right? If you look into other successful standards, we have, the first generation of the specification is not the end, right? It's a good starting point. After that, we build on it. PCIe is currently at the 6th generation. CXL is of the 3rd generation. So new and new usage models keeps getting added, more and more capabilities come in. So this is just the starting, and we're going to look into doing other protocols, other advanced chiplet form factors like 3D, chiplet management, and many more, right? Once the consortium gets, the industry really innovates on a well-defined standard mechanism. The usage models that are supported by UCIE on the left side, you see, which is the standard SoC package level construct. So you got your processors. These could be the most advanced process node. smaller chiplets, whatever number of cores you need, you put as many number of dies, chiplets there. You can have some number of accelerators, some in the most advanced process node, some in the more established process node. You can have your memory and IO controller. These could be used for multiple generations because they don't change as much. You can have on-package memory. You can have other things like, co-packaged optics for optical, and you can have some other analog chips. All of them can be packaged, connected to each other through UCIe. Mix and match, basically. And as far as the bespoke solutions are concerned, you can do this mix and match as to how many of each type you are going to put there, and it just works. The other usage model, which is, effectively, how do we take these goodness of UCIe and extend it beyond the package? So the picture on the right shows a rack, and you can have multiple racks in a pod. And what you see there is a bunch of in each rack, there are a bunch of compute drawers, and they are like full-blown servers, right? And you can, within that, the packages that exist, if those are UCIe, and if you look into the, the green colored ones, they can be your co-packaged optics. So what you have is a view where you got each of the packages in the drawers, be it compute drawer or memory drawer, you're basically sending co-packaged optics based on UCIe. You go off to the other side, and then you get a pool of accelerators or a pool of memory. CXL is defining how to pool resources across multiple servers. So that way, you don't have memory that is necessarily, or accelerators that are attached to only one server. You can then, if you put them in the pool, then different servers can access them at different times based on the need, and they can release it back to the pool. So UCIe is going to enable those through things like co-packaged optics or any other innovations that comes along. It's more forward-looking, trying to make sure that those kind of usage models get comprehended. And remember that we do map both PCI and CXL into as our protocol. So that helps in that regard. So these are the key characteristics and metrics, and I'll let you read through this, but there are two swim lanes. One of them is the advanced package. The other one is the standard package. The frequencies and then the widths are given there. The bump pitches ranges are given there. Anything you design within any of the swim lane, it's going to work across that entire range. So for example, if I design for 32 gig as my highest speed, I must support all the other data rates, 4, 8, 12, 16, 24. So that way, if somebody has designed for 16 gig, I still work with them at the 16 gig data rate. So that's the idea. And these are the different channel rates that we do. Let's look into some of the KPIs. So there are two aspects of bandwidth density. One is the linear, and the other one is the area density. And you will see that, these numbers, there is a range of numbers for standard package and advanced package. So for example, if you look into the advanced package, you are going to get at 45 micron is the number we have assumed. You're going to get, at 32 gig, you're going to get for each segment, it's 64 lanes, you're getting about 1.35 terabytes per second, right? Per square millimeter. Or if you're in the standard package, you're about 125 gigabytes per second per square millimeter. Now let's contrast that with what do we get on the SerDes kind of interface like PCI Express. Your numbers vary, but those are, around 10 is the number, right? Some can get 12, some will get a little less, but if you do a round number, it's 10. So you can see that these are orders of magnitude better density. And why is that? That's because we have taken a lot of work we have done to effectively optimize for the short distance that we have. So that's where a lot of this specification that goes into the die-to-die adapter as well as the physical layer that I showed, that's where it comes into picture. As a result, now if you merge that with the co-packaged optics, now you got a very good solution where I can escape my package with co-packaged optics, delivering these kind of bandwidth density, and that enables a lot of very interesting usage models. If you look into power efficiency, the numbers are 0.5, 0.25 picojoule per bit. Compare that with external interconnects like PCIe, right? I mean, off-package kind of interconnects. And those are anywhere from 5 to 10. So you're getting an order of magnitude better power efficiency, which is what, again, you would expect because these are shorter distances. But the most important one is the next row, which is the low power entry and exit. So those are less than 1 nanosecond. If you look into any SerDes, You cannot turn that SerDes on and off on a dime, right? If your SerDes is off, for the time to retrain it back, it takes many microseconds. Here, it takes me less than a nanosecond, so I can just turn it on and off, and I'm getting about 85% power savings, right? So effectively, even though I don't start with the zero line, nothing goes to zero when you're going to have some leakage power and all. It's getting very close to that linear line, which I couldn't otherwise get with my external interconnect. So what it means is that if I have a 20% bandwidth demand, I can come very close to 20% of the TDP power that I consume. So which is a pretty good thing to have. And of course, latency you would expect to be low because it's an on-package interconnect. And reliability, which is measured in terms of failure fit, which is failure in 1 billion hours, it's pretty low. It's close to zero on the interconnect part, right? So it's about 10 to the power minus 10, which is practically zero, which is where we want it. We want it to be significantly less than 1. These are the list of promoters, and you can see that like any consortium, we start with PCI SIG, started with about 6, I believe. CXL, we started with 9, right? PCI SIG grew from 6 to now 900. CXL is now from 9 to 200, so more companies join in, and we are having a lot of companies join. But these are the initial promoters that made the announcement in the March of this year. And basically these are the leaders, the who's who in the field of semiconductors, packaging technology, IP providers, foundries, cloud service providers, right? So that's critical. That shows that there is a lot of industry momentum behind it. And again, this is the summary slide. I won't read through it, but the journey is just starting. And as I said, it's an open consortium. Anybody can join, just like PCI SIG, just like CXL. And this one is not the end of the journey. It's the beginning of a long and fruitful journey. Questions, sir?
Thank you, Devendra.
Yeah.
Some quick questions. You talked about the physical layer. You talked about the bump pitch. So is the bump pitch and the pinout defined for each of the 2 different types of packages? I mean, are those nailed down by the spec, or is there some?
Yes. So we define the bump map for each of those packages in the UCIE spec. And the other interesting thing is that within those ranges that we have defined, you can design a die with 25 micron and another at 55 micron, and they will still interoperate.
Okay, great. In terms of overall strategy, I mean, you used examples for the high performance computing data center, but is it also going to be applicable, let's say, to consumer devices, or what's the target for the spec in terms?
The target for the spec is the entire compute continuum, everything from your handheld devices to your high performance computing. Everything is comprehended. So for example, if you have your handheld devices, right, you want to still have different types of chiplets, people still put them together. And this will enable you to do that. Just like PCIe is there in the handheld devices, it is there in your servers, it is there in your supercomputers. This is going to be there across the board. Of course, the scale and the size at which you're going to deploy, you're going to have more number of lanes and all of that. In the other case, you might have less number of them, but that's the reason why we have built a scalable architecture that can scale across the board. Yes, but absolutely, the intent is to have this interconnect be applicable from handheld devices all the way through the HPC.
Okay, got it. A number of people commented, at least what you're showing is 2.5D integration. Does the standard support 3D? And then there's questions related to, can you make it compatible with high bandwidth memory, or is there a new or we're going to need a new memory stack to go with this?
So those are 2 different questions. So let me answer them one by one. So 3D, that's definitely one of the things that we are looking at. It's like anything else. We start with 2D, 2.5D, and then we move from there into the 3D. 3D has got its own set of challenges. So we want to discuss that as a broader consortium and do the right things for that is going to be applicable across the board. On the other issue of memory, as you saw, we have CXL.memory. So you can definitely put the memory controller on the other side and have memory attached to that. I believe the question was, and it's a philosophical question, and we are also still discussing that in the consortium, is that, memory controller moving away from the CPU onto the closer to the memory die. In other words, you have a separate memory controller die, right? That's controlling the type of memory that you have. That gives us the flexibility and all of that. You're basically independent of the memory technology, so to speak, right? Is there a play here for UCIE to have some form where the memory controller is on the other side, meaning on the SoC side, and from there you are controlling a bunch of DRAMs and stuff like that? Is that something that UCIE wants to do, or do we say that, hey, that's not an important immediate problem for us to solve? Those are very much in discussions, and we will be. It will be, like I said in there, if you notice that I said that there are future, I had a little note that said other protocols, for example. So think of it as that comes under the purview of the other protocols. There was a question around 3D. So those are definitely in the future in terms of the types of things that we are thinking about. And by the way, we are going to do, just like we did this in CXL, right? We did a set of things for 1.0, 1.1 that was important, that gets the ball rolling. But if you look into 2.0, we looked into and we captured a lot of very other interesting usage cases, and 3.0 is extending that further, right? And same thing happens with PCIe. So that's why I said this is the beginning of the journey. It's by no means, all that we are going to do. It's just the start.
Right. This is really great. It's really helpful to have this overview of the UCIE. I think there's a bunch more questions, and I think many of them are probably better addressed at the panel level. So I thank you very much for the presentation. And once again, I'd like to thank the sponsors who made this event possible, Advantest and ASC Group. Advantest having high customer satisfaction surveys over the last 30 plus years from VLSI Research, and the highest ratings in the last 2 consecutive years. So congratulations to Advantest. And thank you to ASC. The chiplet era has begun, and as we've talked, heterogeneous integration will play a vital role in bringing chiplet-based designs to market. And they are working on the advanced packaging technology and working with everybody in the ecosystem to make it happen. The future is heterogeneous integration. And with that, I will thank everybody for joining us and look forward to seeing you at a future MEPTech event. Have a good rest of your day. Thank you.